I think we're ready to go. So my slide says good morning, everyone, because I didn't update my notes. So this is still all my notes from my previous talk. So I won't be using them. Otherwise, we'll definitely have confusion today. So good afternoon, everyone. Welcome to my talk. Today, I would like to touch on a vulnerability called Dependency Confusion. My name is Tinus. I do research, consultancy things. It's been a while in the cybersecurity field and just honestly enjoying it. So with that being said, I think let's dive directly into it. So you might be confused because we're going to talk about DevOps today, not actually red teaming, but in the end, we'll tie it back again to red teaming itself there as well. I think it's worth sort of having a conversation around how development has changed over the last couple of years. Some of you might remember words like the waterfall model, and then all of the buzzwords that followed after that, like Scrum Master and Agile and moving blockers, and I don't know. It's a wild field out there, but the key point that I want to focus on is that I think in today's time, we have moved over to a lot of automation, right? In the past, it was a manual process. You would develop code, you would test code yourself, right? And then afterwards, you would go through the various stages of deploying it into different environments, testing again, and once you're happy, again, a manual process that you're following to migrate that over. And in today's time, a lot of that, if not all of it, is automated for us, right? We have basically what you can call a CI/CD pipeline or a DevOps pipeline, and now the new buzzwords are things like DevSecOps to care about security of the pipeline and in the pipeline and all of those different things. But the key that I want to focus on is that automation element. And what that changes for me is that no longer is the end result the only thing that threat actors can target, right? Because there's automation introduced, because at this point it's not just about compromising a developer, but compromising any of the technologies that are being used in that pipeline is actually going to allow you to get to that end, to get into production, where it might have been in the past just a vulnerability that you had to exploit, right? So the attack surface has grown significantly. Now, for today, we will be using the following pipeline as a demonstration. I know it's not fully complete. I only have one environment with production, right? So I'm cheating a little bit by going directly to production, but bear with me. For this pipeline that we will be using today, we have a developer, they're using a workstation. There is a VPN that they use to connect in, and essentially in this case, what we are saying for security is that this developer only has access to GitLab, right? They should only have access to the source code. From there, automation takes over, and we're hoping that the security of the automation is going to deal with it for us. I'm also using a GitLab runner. There's a bunch of other things that you can use. GitHub has GitHub Actions, for example. I like GitLab because you can host it on-prem and do some interesting stuff with it. And then basically what is happening is we will be basically talking about two different packages. One of them is a Python package, so a Python library that we are using that we're storing on a locally hosted PyPy repo, and then or registry, and then we have a Docker image that gets built, and that's basically a Flask application that we are going to host into production there as well. And as you can see from the CI configuration, we are basically going to talk about 4 different stages. So we have the prepare, the build, the deploy, and then the test stage that's going to execute today. So let's quickly take a look at what that is actually doing. That website, for any of you that attended Ethan's talk, he is to blame. He set up this network and decided that the best application he can come up with is one that's actually doing translation between my messages and his there as well. So what we are going to do here is we'll see that we have the different stages. For prepare, we're basically going to kill that Docker container. Build, we're going to actually compile the code, and then we're going to deploy it, and then we're going to run some tests. And those tests are important for us because with the test cases, we need to make sure that the code is actually working, right? So what I'm going to do is I'm going to add some more Gen Z words there for translation. So just following through with what he gave me there. So we'll do a little bit of a translation, we'll do a commit, and then once we do a commit, that GitLab runner is going to pick it up and it's going to execute that CI script for us there. So if we quickly take a look there, we will see that the new one is running, and we'll see that the 4 stages themselves are in action there. So that one should complete quite quickly, just stopping that container so that we can do a rebuild there, and then just give GitLab a little bit of a time. And there we go. We can see that it's starting to do its build. Basically, what that process is doing is it's creating a new Docker image, and that Docker image is compiling the Flask application, but it's also, before that step, it is going to install the actual dependencies that are required for that Flask application. And one of those dependencies, and that is what we're going to focus on today, is a pip package that it needs to pull from that internal PyPy registry. And we can see, very importantly, that the test case actually succeeded. That's the important part there. It's worth noting in today's time, even your unit tests are automated as well, right? And if your unit tests don't succeed, then immediately the rest of the pipeline is basically going to stop. I know I misspelled surprise. It was very early in the morning. But we can see that the translation works, the app is working, it's recompiled, and basically we are in the new environment there. So, taking this into consideration, basically we have to ask the questions of how would we go and approach to attack this? I talked about a larger attack surface. What does that actually look like? So if we're not looking for vulnerabilities in the actual application, what are we looking to compromise there? Now, there are quite a lot of research that's done about this specific thing. I would say that there's 4 main elements that you can look at. You can, for example, inject into the source itself, right? Maybe you're lucky and basically you're making a pull request as a contributor, sneaking in a little bit of vulnerable code there that goes undetected, and now all of a sudden you've injected into the source code and your malicious code, it's going to make its way all the way through. I don't know who of you, for example, followed along with the linpeas.sh one. That would be the other one, commit as a maintainer. He's just a friendly guy looking to get some stats, right? And all of a sudden, if you're using linpeas.sh, you're now sending what might be client or confidential data off to some random server, basically for someone to collect that information. So not a great idea. You can inject into the repo system itself. Can you compromise credentials? Can you get tokens for it? All of those wonderful things. Looking to exploit vulnerabilities in any of those software stacks as well. So again, it's not just about vulnerabilities in production, but if there's a vulnerability on GitLab, if there's a vulnerability on Jenkins, on anything that is being used in that pipeline, you might have the opportunity to, again, inject into that attack surface. There's also injection during the build, but most of that is around compromising the build system itself. And you'll see when we touch on dependency confusion, this is a little bit of a different vulnerability there. Or we can look to create a new package. There are things like, I want to call it package squatting, like typo squatting. And if you read sort of some of the articles out there, it happens a lot. All of us have fat fingers when we're typing a pip install or something. And if you make one mistake, like numpy becomes numpy, all of a sudden someone has registered that package and it's a malicious package and it's going to execute. And the reason this is so important is because, remember, your build pipeline is essentially code execution at that point, right? It's actual code execution that is happening there. It has a lot of privileges. It's intended that way, right? The answer is not to make the installer less privileged or to reduce functionality, because it needs that, right? It's actually installing a package for you at that point. But we are not going to look at any of these. What we are going to look at is a vulnerability called dependency confusion. Now, this was originally published in 2021. Show of hands, any of you know of this vulnerability? Heard of it before? Okay, so we have a couple of people here that has heard of it. When Alex found it for the first time, he was able to compromise Apple, Microsoft, Tesla, and PayPal at the same time. He racked in $120,000 in bug bounties in one go. So quite a powerful one out there. Apple didn't want to give him the maximum one. He was like dead sure he could actually compromise everyone's Apple device, and they were like, no, you're stretching a bit. But I personally believe him when he says that as well. And essentially, this dependency confusion vulnerability stems from the issue that your package managers, when you are performing an install, right, they are getting the packages from multiple different locations, right? So it's not coming from a single location, it's coming from multiple locations, and then essentially the package manager needs to decide which one to install, right? And this specific vulnerability comes from internal and external dependencies. Now, there's a lot of debate whether a package is an internal package or an external package. For today, what we will be focusing on for this distinction is, did you develop this dependency yourself, and are you self-hosting it? Or is this a dependency that someone else has developed and they are hosting it? If you think about something like jQuery, that's going to be an external dependency, right? You did not write jQuery. I hope the author of jQuery is not here, right? But you might be using that package. But let's say for your business, for example, you have a package that you are using for authentication, right? You want to standardize the process of authentication. You're going to create a library or a dependency to deal with that authentication once, right? And then you're going to self-host that package, because now it's going to be nice and fun. Whenever there's a new project that you're developing, you can use that exact same package in those cases. So how does dependency confusion work? Well, it's about winning the race, right? And as you'll see here, the race that we are talking about is a race of version numbers. So let's say we have the following environment where we have production, and then you'll notice that we have two different Python or PyPy registries, right? We have the external one, which is pypy.org, and then we have the internal one of pypy.lock. That's a registry that we are self-hosting with our own packages that we are creating. So what's going to happen is that the attacker needs to learn the name of the internal package or internal dependency. And we'll touch on the various different ways in which you can learn that name. Some of it is super simple, some of it might be a little bit harder. But I want to make it clear, the attacker doesn't need the actual package. They don't need the source code of the package. They only need to know the name of the package in question. So after they learn the name of the package, what they are going to do is basically upload the same package name to the external PyPy repo, right, with a higher version number. That's where the trick comes in, right? We upload it with a higher version number. I always choose version 9000, so I haven't seen a lot of software that reached that version before. And then essentially what's going to happen is your build infrastructure, at the point where it needs to run that install, it's going to collect the packages from multiple locations. And it's going to see, I have the same package being hosted internally and externally, so which one am I going to install? And the decision comes down to the higher version number, right? On most of these things like pip, gems, npm, it's choosing the higher version number to install in that case. And all of a sudden, what's going to happen, right, is the build will occur with the package version that's a higher number, which is the attacker-controlled package, right? So without knowing the source code, without knowing anything but the name of the internal package, I now have the ability to essentially get code execution at the build stage, right? And then essentially, using some very nice techniques, we have the ability to essentially take that malicious package and infect the pipeline moving further. And that's the part that we're also going to focus on a little bit today. So before we touch on just showcasing the basic pipeline of this, let's sort of look at how you're able to learn a package name. Stack Overflow is my favorite, right? So you'll see here that basically we have someone asking a question and divulging a little bit of information about their specific packages, right? And here we can see that we learned the name of their internal package, which is the Gen Z translator. And what's nice about this, and this is for the further attack, we also want to learn a little bit of information about the internal PyPy registry itself as well. You can either learn that externally, or there are techniques to enumerate that when you infect with dependency confusion there as well. And then where we can see that the issue comes in is with the pip install, and we'll touch on that for the mitigations as well. What they are doing is they are saying extra index URL. So what that is saying is, rather than forcibly download from one location, add another potential location where this package can be downloaded from, right? So now we know the name, and we also know where the internal repo is going to be stored there as well. There are other ways that you can find it. So before this talk, I basically ran a search for -- extra - index URL. Not a lot of repos, only 18, but about 64,000 issues. So reading through those, finding a couple of package names, finding a couple of vendors or sort of places that are using packages, you'll definitely be able to find a couple there. It's also worth noting when Alex found this one first, with his search, he was actually able to infect .NET, all of its versions, which is why Microsoft also paid him out a bug bounty there as well. And you can actually still see, if you go to that commit, you can see that they actually fixed it to change it from extra index URL to index URL. So they were properly vulnerable. And I mean, if you were able to infect .NET, that's a couple of people that's in for a bad time. And then very important, we're focusing for this talk on Python packages. But as I mentioned, this can happen for Ruby, so with your gems, and with JavaScript with NPM, it can happen there as well. And what Alex also found there as well is that a lot of the times when you do a NPM compile, in the JS files that gets generated, sometimes it actually discloses the names of internal packages that are being used. And that's another way that you can go about when you enumerate a web application to actually learn those package names there as well. So, how are we actually going to do remote code execution? For that, we need to talk about what do you need to create an actual Python package, right? And we're going to keep it very simple. Basically, if you want to create a Python package, you need a setup.config file, you need a setup.py file, and then you basically need the package, and you don't need a main, but I think you're a savage if you don't have a main. So you need a init file, and you need a main file. That's it. That's a bare metal, the simplest package that you can have. And what we are going to do for remote code execution is essentially in setup.py, we are basically going to make use of what's called the post-install scripts. You have pre-install, post-install, pre-develop, post-develop. What these hooks basically do is they are hooks meant for you to execute additional commands after a certain step in the package installation. So one that any of you that do offensive security might know, if you look at the in-packet tools, right? After you do the install, miraculously from terminal, you can just call the file, right? You don't need to go to the location where they're installed and then use the files. That's a post-install hook, right? Basically what it's doing is it's doing a rebind of where the packages were installed to a bin, which means that you can essentially use them. So there's legitimate reasons for having these hooks. But we can use these same hooks because Python is also code execution as a feature. You can import OS, and from that point, you can do whatever you want. So we are going to inject into that specific section of the post install for us to get code execution. So let's quickly take a look at what that looks like. So you'll see that here we are basically going to create our package. So we'll start with a config file. Very simple, just a little bit of metadata about where to find stuff. It's just going to pull that config file in there as well. And then what we'll do is we will create two files. So the first one is our init file, and we're not doing any code execution or anything here. We're just simply creating two basic files. I'm also going to populate main, but this isn't a requirement for the package to actually install. Both of those can simply be empty files there as well. And then it's just going to be a little bit of painful because none of my you're going to see none of my tools were actually set up at this point. So I'm quickly going to have to install Twine and also sdis for my installs there as well. But what you'll see is we're currently doing the imports. We're going to set our version number to 9000.0.1 because I'm pretty sure 9000 is going to win the race. And then we're basically going to copy over our package name there as well. And then let's start with a little bit of code. So we'll do our post install. And for this one, we're just going to go with a Python reverse shell. I think it's going to be an ugly reverse shell. You can see there in the command class, we're just specifying for install to hook into the post install there as well. And for this one, we'll just do a simple Python reverse shell that is going to get executed. I know this is wild because I'm running os.system in Python to run Python again, to run import OS, to then again run a shell for me there. But it works, okay? So we're going to do that. Then we're going to try to compile. We're going to fail miserably afterwards. And then we'll quickly get the right and relevant stuff. Sorry, that did not mean to happen. Hold on. There we go. I just need my mouse. I'm going to skip forward there. Okay. There we go. Skip a bit forward. Okay, cool. So basically what we are going to do there, on that note, when you run the -m build, it's going to build both a tar file and a wheel file for you. You can't actually get code execution with a wheel file. The first thing that I had to learn is if you want code execution, basically what you're going to do is just delete the wheel file and only upload the tar file. Then anyone that gets your package is actually going to get code executed. So it is really that simple. Okay, so now let's quickly go. After sort of creating the package, we uploaded it to PyPy. We're going to add another Gen Z word just to showcase that the pipeline itself is going to execute. Can't remember all the words I added. That is sus. Cool. Okay. And let's go. Let's have the pipeline execute. Let's give it a little bit of time. Okay, prepare should be done by the time we go into it. And then essentially at the build stage, what is going to happen is that at the build stage where it goes pip install with the extra index URL, at this point it's going to find that package both on pypy.org and on the internal repo as well. And what you will see there is that we have a nice shell. But it is, no, don't clap, because the shell doesn't work, right? It is absolutely horrendous, right? And this is part of the problem, right? Because basically, I got a shell, yay. The question is where? Where did I get a shell? Number one, that's where the confusion part of this entire talk comes in, right? It's red teaming, but you don't know who you're compromising. So I don't know if you fully can go this route, right? But it's worth noting as well, I hope that all of you noticed, is that essentially we were at a standstill, right? That entire build process did not continue at the point that I have a shell. Now that's my bad. I need to create a non-blocking shell and everything like that to at least have the code still execute, right? But it's great. We got that to work and we can see, and then all of a sudden we fail test. Anyone have an idea why we failed that test? There we go. We don't have the source code, right? Because we don't have the source code of the original package, right, at the point where the unit tests execute, at the point where it runs the import for the package, nothing happens, right? We will 100% fail every single one of those unit tests, right? And this is where I personally believe dependency confusion died a slow death, right? Why everyone was like, great story, bruh, but not going to happen. Not going to care about it. Not really going to do anything about it. Because in essence, we will know 100% at the point where dependency confusion is happening because the build stage will freak out. At most, if you're able to compromise something like a developer workstation, which is great, but right at that point where they try to run the code, which is the next step after compilation, right, essentially they will figure out that something is wrong. So that is the issue for it, right? We can see that the test case, the unit test, has essentially not executed, right? And in this case, we got remote code execution in a Docker agent that's currently running a build. Like, it doesn't really help at that point, right? It's going to immediately be detected, and the best we can essentially hope for is going to be for a compromise of a workstation. So this was about 4 years ago when I played around with the vulnerability, and I found a better way, right? So 4 years ago, I found a way that you can actually get past the entire build stage, and you have a way to essentially blast through to production. I don't want to publish it because I didn't feel that it's ethical that that information is 100% out there. It felt a little bit iffy, so I decided to basically just leave it. So if you go look at, for example, some of the training that I did on dependency management on TryHackMe, you'll see that's where it stops, right? Shows you how to get remote code execution on a Docker container, and I feel like that's it. We can leave it there. But it's always been bugging me because there are actually ways that you can get fully through to production, or there were. Let me make that very clear. There were, and then there was some trouble this week. But basically, we have a post-install hook, right? And we are in the exact location where a pip install is running, right? So why don't we actually use this, right? So this led me down a path 4 years ago where I essentially investigated how does pip actually install packages, and how does pip determine whether a package is actually installed, right? You just see succeeded or failed, right? And that's not always just determined by like errors or things that go out there. Like what actually tells pip that a package has successfully installed? So what we're going to do is we're actually going to do a couple more steps. And essentially what we are going to do here is that we need to find a location of what's called the egg file. So pip, until recently, I need to keep saying that caveat, basically what they did is they would essentially look for an egg file. The egg file would be placed in the directory where it installed the package, and that egg file, upon exit from pip, it would read that one, and if that file A exists, and if it has the right information in it, it would say, cool, package has successfully installed, right? And we move on our merry way, we have a pip exit that succeeds. So what I basically theory crafted and created is, what if we, A, save the location of where that egg file is, right? When it's installing our package. Remember, this is post-install, right? So we save the egg info location, and then we run pip again to uninstall ourselves, right? So let's uninstall our malicious version, and then let's actually fix the code that they made a mistake in. So rather than using extra index URL, let's use index URL. So we force it to use the internal repo, right? And then once it's actually installed the correct version, the only thing that remains for us is to take the correct version's egg file and replace it in the location where pip is actually looking for our malicious installs egg file, right? And there you go. All of a sudden, we're solving a couple of problems here. Firstly, pip is not going to error out because it's essentially going to find the install has succeeded. And now also we solved that massive problem of not having access to the source code, right? At this point, if this has executed, what is going to happen is that we will have actually installed the legitimate package. The unit test cases are going to run. All of them are going to succeed. And if you're not like me, writing an os.system command, right, but actually sneaky with your persistence, you have the ability to embed persistence and wait until this package that is compiled makes its way to production. And at that point, you execute and you have code execution on production. And if you ask me, I would love to see the faces of an incident response team that has to deal with that. Like, where do you start, right? Like, where's your logs to tell you that production is infected all of a sudden with a persistence mechanism? Like, how do you trace that back to the actual build stage in those cases? And what's worth noting here is we're also leveraging something, and that will become important. We know for a fact for something to be a pip package, the one file it always has to have, the init file, right? So you embed your persistence in the init file, right? And only savages write in the init file, so you are 99.99% secure that the actual package won't have code in the init file, right? It shouldn't. It should be an empty file. Every tutorial you read tells you it's an empty file, but it executes as soon as you import the package. So that now means we embedded persistence in an init file, so we're not overwriting any of the sensitive code. And at the point where they run import package, our remote code execution is going to execute. So this worked for 4 years, and then Monday morning, 1 o'clock, none of my pipelines worked. That one pass is where I reverted back to just normal stuff. I got failed, and I didn't understand why, right? So I promise you this exploit worked for me. I'm now standing like shilling like snake oil here because it worked for me for the last 4 years. And now all of a sudden, a week before my demo, Python decided, nah, not going to happen. Every single one of my pipelines was failing. And I actually had to do a little bit of an investigation. And it turns out Python doesn't use egg files anymore at all. So the entire principle of my compromise was gone, right? Because now, essentially what Python is doing, and more so importantly, pip with the later versions of it, is that essentially it's no longer using the egg file, it's no longer distributing the egg file to the install location. Instead, what it is going to do is it's going to build it in a temporary location, right? And then use that egg file to compile a dist, which is that dist info that you can see there as well. But they were not done screwing me over. The other part that they also screwed me over on is post-install is no longer post-install. You can do some funky stuff with threads and you can get very, very close, but they actually learned that it's bad that the actual package gets fully deployed and then post-install executes. So what they are doing now is essentially post-install is the very, very, very last step before the wheel gets compiled and the wheel gets dropped, right? So you physically can't do post-install anymore, right? Like you did in the past, it will always, after your post-install, that's the step where it's going to run the compile step, and then it's going to do the deploy step. So that's an issue, because remember, our entire path to get to production relied on the fact that we can uninstall ourselves, that we don't need that code anymore, and we can replace it with a legitimate version. So it was not good. I had to decide what we are going to do for today. And essentially, I was this close to contacting Charles and saying, like, I'm out. I think you need to find someone to do a talk in last week. This was about 2 o'clock in the morning, and I said, well, let's try. We did it once, we can find it again, right? So let's go back to the basics of what is actually happening here, right? So now, as I mentioned, post-install is going to execute before the compile and deploy. So you can see that after copy is me doing a print, right? In the post-install phase, after the install has run. And you'll see only after that is it building the wheel, creating the wheel, and then deploying it. So you physically can't, and trust me, Python does not like threads, and I gave it so many threads to try and get past that point. You physically can't get past that point, right? The last steps that pip is going to execute is compiling that wheel and then deploying it for you, right? But it's worth noting we are still in the position where pip is used. So we can still do this, right? We just have to be a little bit smarter. So essentially, we're going to change a couple of things, right? The first thing that we're going to do is that immediately now we are going to install the correct package. Why? Because remember, it hasn't yet compiled our wheel. The package doesn't yet exist, right? So when you run pip install and a pip install, right, it's actually going to install. So this is going to install the correct version of the package and deploy it. Okay, that's great, but remember, it's going to compile our package and it's going to overwrite that version, and we don't want that. So what we are going to do is we're going to determine where it's actually running that install. That ls-al, I know it's bad OPSEC, that was sanity in like 3, 4 o'clock in the morning, right? But what we are going to do is essentially we will embed the persistence in that package. So we're still going for in the init file of, remember, this is the legitimate package. I know we're all confused, myself as well, right? Let's keep this together. Okay, this is the legitimate package. We are embedding persistence in the legitimate package. Our malicious package has not yet installed. Are we all with it? Cool. Okay, great. Then we keep a backup. Okay, that's very important. Keep a backup of the legitimate package, because remember, we're going to overwrite it, right? So essentially, we keep a backup of the legitimate package, and then this is where the second part comes in. In our malicious package, we are now going to be a savage and actually execute code in init. So what we do, remember, it's now going to compile our malicious package, and then essentially it's going to overwrite the legitimate package again with the malicious package. But now, in our malicious package, what we are going to do is we are again going to find a location of where we're installed. We're going to run pip uninstall now. So it's very interesting when your package is loaded into memory, right? That's the point where you can actually uninstall it. It doesn't need the files anymore. It's not like a Windows system that locks the file. Once Python has run it in memory, it's perfectly fine. So we're going to uninstall ourselves. We are going to flush that directory into oblivion. And the reason we need to do that is because pip is not actually going to do a full replacement of the legitimate package. It is only going to overwrite files that match in the original one and our malicious one. And remember, we're keeping things minimal. We only have an init file. So technically, the normal package is already there, and we've only overwritten the init file, but for good OPSEC, we actually want to remove ourselves, right? So we blast it, and then we take the backup that we kept, and essentially we take that backup and we put it in the location where it's expecting it, and now we're done. We basically have the legitimate package in the right place, so the unit tests are going to work, and we have embedded persistence. Crazy. Let's watch it. Cool. Okay. So essentially, just to showcase it again, we basically have our install where we are fixing the code for them. So instead of extra index.url, we are using index.url that forces it to install from the internal location. And then what we're going to do is we are going to embed into the actual one, and notice the little ampersand. I learned my mistake, non-blocking, right? We want that shell to execute, but the rest of it to still run. And then as mentioned, we are going to keep a safe backup of that code. And then worth noting, just again in our init file, what we are going to do, find our location, uninstall ourselves, nuke the directory, and then copy the backup to the legitimate location that we need it to be in there as well. So with all of that being said, let's actually, now this is like 4 or 5 o'clock in the morning. Let's actually add another word. You can see I even deleted sus. I was reverting code as much as possible to try and get this back. So let's add another Gen Z word, and then let's actually see that we blast all the way into production. I don't know. Don't ask me. This is for Ethan to understand. Do not ask me why these are the words that they are. Okay, so let's look at our pipeline. You can see all of my miserable fails before that there as well. And let's see what it's going to do. So the prepare stage is going to run. Then let's look at the build stage, what's going to run here as well. Okay, here we go. Should install our package now. Let's go get our shell. Now, worth noting here, we're passing the build stage without getting a shell, right? Which is expected, because it should do the right things as soon as the package executes for the first time. So there we can see that essentially the entire build step has succeeded. Let's quickly make sure that the steps are there. And you can notice there that it says that it installed version 9032, a lot of versions. But you can notice that it actually installed 0.1.3, which is the actual package. So let's then see the test stage. We can see that the test passed. So this means that our entire pipeline succeeded. And this time, we have a shell, and one that's worthy. So finally, we actually have a shell in production. And just to show that the actual application is working as intended, and it is doing what it should. Lots of sanity loss, but we finally got there as well with everything working. Okay. Now, on this note, just a couple of things that I want to finish on here as well. The reason I believe this is quite a potent attack for you to perform out there as well is that there's not a lot of information given to someone that this is happening. You saw the build stage completed as normal, and you saw that one line that it basically mentioned that a different package was installed and then the correct version package was installed as well. It's worth also noting that I was running pip in verbose mode, which I don't think a lot of people do, right? If you don't run it in verbose mode, you lose even more of the OPSEC there. It's not even going to tell you that it found 2 versions. It's just going to blast through and it's going to do its install. Okay. Now, it's worth noting that the same vulnerability for dependency confusion is something that you can find in both gems for Ruby and then also in NPM as well. And this is part of the rest of the exploration that I want to go on there as well. For NPM, you have things like pre-installs, installs, post-installs, so different places where you can inject. And again, in a lot of those cases, right, that race condition is going to happen of the higher version numbers, right? Most package managers are configured to use multiple different sources where it's pulling its packages because you have both internal and external packages in the mix, right? And if you can create this confusion, the higher version number is going to win there as well. So what can we do for mitigations? Also, if you were at Ethan's talk, you'll notice the difference between mitigations and remediations, right? And that is because I don't really think there is a full-blown remediation for dependency confusion. Because everything you're going to do is going to have something else for you to think about and something to do, apart from the last one, which I think is a pretty decent one. But essentially, the first thing we can do is we can basically lock the repos or the registries, right? So we can split out our lists and say, these are the installs for internal dependencies, right? These are the lists of external dependencies, and run them as separate steps where you're pointing it directly to a specific registry where it needs to pull the package from. I think it can work, but that's been one of my biggest gripes with the entire fight between index URL and extra index URL. Like, I can fundamentally understand why you would want to just add another registry and not necessarily lock it down to one single registry, right? If you just look at how anything works, it has multiple locations, right? Because one location can fail. So it makes sense for me why certain people want to do something like an extra index URL. One of the things you can do, and this is a surefire way to fight against this, is version pinning, right? So in your packages, you can pin them to a version, and there are a lot of people that do this. My personal issue with that is it becomes outdated, right? As soon as you version pin, you're going to version pin into oblivion, which then means if there is an actual vulnerability in the package, you will not receive that update there as well, right? But if you version pin, you are telling pip it needs to look for this exact version there as well. The other thing you can do is, in certain cases with the package managers, you can tell it to change its priority. This is not something you can directly do, for example, in pip, but if you're using something like JFrog Artifactory or Azure DevOps, you can actually tell it what is the priority of searching for packages there as well. But then you need to basically rechange the priority to be that it's not version number based, but sort of the priority of which registry it's going to hit first. And then the other thing that we are seeing, and I personally believe that this is one of the best remediations that you can do there, is if you have internal dependencies, register the package name externally there as well. Claim that space, right? And what works really, really well with something like NPM is you can register the name of MWR. And then all of your packages can be MWR.this package, MWR.this. Because you own the name MWR, no one can essentially register a package that starts with MWR dot. So you own that entire top namespace for all packages in that location. So that's something that you can do. But then again, you need to make sure that all your developers are actually keeping to that convention and using that namespace for their packages there as well. And then just lastly, to end off on what are the detections for this and what can we do here? I think you can hunt for the vulnerable installs. Like I showed you, -- extra index URL is one of the things that shows it. Whenever GEMS has a source or NPM has a -s in the command attached, you know that they're adding additional registries there, and you need to do some sanity checking there as well. And then the other thing that I realized, looking at it and looking at the logs that I have in my actual build output, is that those pipeline logs are crucial. And I hope that we can go to a stage where you can do stuff like a pip install verbose, as ugly as that is and as much information it generates, but that log files of our build stages actually plays a large role, right? And it's not just enough to have logging in production. We need to have logging that goes through that entire pipeline there as well and keeps that information for us. And this is not just for dependency confusion, but for other pipeline attacks out there as well, right? As soon as there's an attack that happens of that actual pipeline, your production logs are not going to be the place to try and piece together what has actually happened there. And then just lastly, thanks for Alex for the initial research. Inspired me to look for this, inspired me to take it further. And yeah, just thanks for TryHackMe. They're sponsoring my AWS bill, which if any of you have AWS, you know it's expensive. So that definitely helps there. Thank you very much. Any questions? Yes. Yeah, I mean, I played around with that a lot when Pip started doing things differently. So I was doing a super of a super of a super to try and get it past that compile stage. I physically couldn't. But I think there's that for me is an interesting part, but a more interesting one that I would like to actually do is exfiltration of the source code of that internal package. Because at the point where you have the source code, you can hunt for more vulnerabilities. And even if they fix dependency confusion, at that point, you actually sit with that source code, which might be intellectual property at best, and at worst has some vulnerabilities that you can exploit there as well. But yeah, I felt very dirty writing code in init.py. It should not be there, but it does work. So yes. Any other questions? Probably the one that it hit first, and I need to check how it depends on that order. But like I say, just version 9000, that's taking you to the moon. Any other questions? Thank you very much.
Across the attack surface, scattered products and siloed views create blind spots that feel unstoppable. The deadliest risks are in these gaps, where attackers move in. It's time to unify fragmented snapshots into one all-seeing view of risk and unleash a platform born with one intention: isolate and eradicate your priority exposures. From IT infrastructure to cloud environments to critical infrastructure and everywhere in between. This is Tenable. Your exposure ends here.